In this video, we're going to walk through the solutions to a few practice problems writing out nuclear decay equations. So we've got 4 examples here, and I'm just going to walk through these. Our first one is talking about the alpha decay of Seaborgium 271, which is a fantastic name for an element. So the first step in all of these is to actually write out my isotope symbol for my parent nuclide. And so for this one, I've got 271 and Seaborgium is Sg. And finding that on the periodic table, and sometimes these take a little bit of hunting, I'll find it has an atomic number of 106. So that's my parent. It's decaying by alpha decay, so I know that I'm going to emit a particle rather than capture something. So I'm going to start off by putting out what that alpha particle is on my product side. So it'll have a mass number of 4 and a atomic number of 2 or a charge of 2. And then I'm going to add my new unknown one. So I know that my 106 has to equal 2 plus whatever my new atomic number is. So 106 minus 2 will be 104. And then for my atomic number, or sorry, my mass number, I know that 271 has to equal 4 plus whatever that atomic number for my new isotope is. So 271 minus 4 is going to give me 267. And if I go to my periodic table and I try to find 104, I'll find Rutherfordium. Rutherfordium? I don't remember exactly how to pronounce it. So that's all that is for alpha decay. And I've got a nuclear decay equation. So let's do the next one. It's beta decay. So I've got hafnium 182, abbreviated HF, and it actually has a atomic number of 72. So it's going to produce this beta particle, which is just an electron. So it doesn't have much mass. It's got a -1 charge or atomic mass. You can use the beta symbol or the electron symbol. And so to have 72, -1 plus 73 would give me would give me 72. So I'm going to put that for my atomic number. And my mass number isn't changing at all because that mass of the beta particle is 0 or rounded to 0. And so 73 is going to correspond to tantalum. I am challenging my ability to actually pronounce our elements, so that's fun. And that's an example of beta decay. So for our third one, we're looking at positron decay, and we're starting with europium 150. Europium has a atomic number of 63. And if we're doing positron decay, it's very similar to that beta decay. It just has the +1 rather than -1 charge. And so we will add that 1 to a number to get 63. And so it's going to have to be 62. And again, my mass number doesn't change. And 62 will correspond with samarium, like this. And that's an example of positron decay. Lastly, let's do an electron capture. So this kind of breaks our pattern. We're going to actually add something to the reactant side rather than have it be the product side. So it's not really a decay in a sense. So I'm starting with osmium 185. And osmium's atomic number is 76. And we're going to add to that an electron. And well, I've been using the beta and alpha symbols since it's called electron capture, it's hard for me not to actually write the electron symbol. So it doesn't matter which one you use, in my opinion. Maybe there are some that disagree. So 76 minus 1 is going to give us 75. So we're going to produce an element with an atomic number of 75, and our mass number stays the same. And so this is going to correspond to rhenium. And that's it. There's 4 examples of nuclear decay equations.